Okay, let's go ahead and get started. It's a little after 2 o'clock by my watch here in Tucson, Arizona. Thank you for connecting to another episode of NextGen Geospatial. My name is Jeffrey Gillen, and I work at the Data Science Institute and Cybers here at the University of Arizona, coming to you live from the Weaver Science and Engineering Library on the campus of U of A here in Tucson. And so in our workshop series, I believe this is week 6 or 7. Wow, yeah, time is flying. So this time we're gonna tackle kind of a bigger topic. I call it reproducible pipelines. Now, whoops.
The home button does that.
Oh, it's okay. I'll just
Now
keep going. Okay, so we're going to tackle a topic called reproducible pipelines. There's a lot of ways to go about doing pipelines, so I'm just going to kind of expose you to one flavor of it. The idea is just kind of show you what it is, show you basically how it works. But of course, there are a lot of details. And with pipelines, there is a lot of details we're not going to cover. We're pretty much just going to hit the highlights and keep going. So there will be a lot of kind of dots to connect. And if you're just like, whoa, what is going on? Please ask questions in the chat or connect with me afterward and we can go into a lot more depth. All right, so let's go ahead and get started. And I'll go to my course content. I put the course content link in the chat. It's the same as always. We organize all of our stuff on GitHub. So this is a NextGen Geospatial course content. Let's go down to the calendar. All right, we've gone through a bunch of topics already. So we got our way through cloud native, and now we're on to here, reproducible pipelines. So it is October 15th. And go ahead and click into that lesson. Okay, here we are. Container, you can call it reproducible pipelines or more specifically containerized pipelines. So what we're going to do today is I'm going to go over a bit of theory on what I mean by a pipeline. What do I mean by containerized? Why is this something we would want to do? How does this help us in geospatial analysis? And then we're actually going to do a hands-on. And you can do the hands-on on your own local machine if you like, or you could do it in GitHub code spaces. So to do code spaces, you'd have to have a GitHub account. But it's really easy to do. It's a free thing. So if you have a free GitHub account, you can get a small allocation of free code space computing, which would allow us to do the demo and allows you to do other kind of testing type of stuff. Or you could just do it on your local machine. So it's kind of up to you. All right. So like always, as I go through this, please don't try to read all the text. I write it like this so people can step their way through it asynchronously. But as we're going through, please just listen to my voice. I will point out graphics I'd like you to look at or specific words I'd like you to look at. Yeah, let's get going then. Okay, so what is a pipeline? So when I say reproducible pipelines or containerized pipeline, let me give you a definition of pipeline. A pipeline, I'm defining here, is just an automated sequence of data processing steps where you start with one thing, you do a process, you get an output, and that output then gets put into the next process, right? And then that outputs something which gets put into the next process. So it's just a step-by-step doing something is how I'm defining a pipeline. And this graphic here is just a very simple concept of what we're doing. We start with input data. We do processing step 1, which then is fed into processing step 2, which is fed into processing step 3, and output, and then you get to like some kind of output product. So this is very common in geospatial analysis, right? You start with some kind of raw data, maybe it's a satellite image or drone imagery or something like that, and then perhaps you have like a goal at the very end, like I would like to produce an NDVI from my satellite imagery, and there's going to be a series of steps to take you from the raw data all the way to your imagery product or the final product you're trying to create. So a pipeline is a very general type of concept. For our purposes today, I'm going to take that definition and make it a bit narrower. In this case, I'm going to say that a pipeline is about automation, and it's about trying to combine different kind of ecosystems of processing tools. So think about combining things like Python and R, or JavaScript, or command line tools like GDAL or PDAL, or other kind of tools that are out there. We can put those all in a seamless pipeline where the output of the Python could then go into the input of the R, and the output of the R could then go into the input of GDAL. So we're not limited to one ecosystem or another. We're not limited to one tool. We can kind of mix and match. There are lots of ways to do pipeline management, or you could call it workflow management. That's another kind of way to describe it. I'm going to show you an example using something called Docker and Docker Compose. There are other ways or other softwares to do pipeline management. Some of those could include Nextflow or Makeflow or SnakeMake. A lot of these things come from the bioinformatics world, where they really kind of perfected one step leads to another, which leads to another, which leads to another. And it also makes complete and total sense in the geospatial analysis world. Like the two fields are very similar, and we can take something and just digitally do process after process to get to what we're trying to accomplish in the end. Okay, so we're going to make a reproducible pipeline using a combination of different tools. That's what we're going to show today. All right, so let's talk about containers. What are containers? Let's start with the problem. Okay, so at Cybers and Data Science Institute, we are very into open science. We're trying to take, we think that anytime a scientist or a researcher makes some kind of intellectual property, they should be able to share it with the rest of the world in an easy way. So that is kind of our goal. If you make a great script, share it. If you have great data, share it. But sharing can be challenging. There are difficulties that can arise when I'm trying to write code that someone else wrote. We have different computing environments. My operating system might be different. The software, like all my dependencies, all my packages in R or Python might be different than my buddy who made the code. So there are reproducible issues or problems that we're trying to overcome. And then we can get to a container as kind of a solution to that. So this is going to be very high level, kind of real quick. Don't get too hung up on exactly how it works. This is more about tell you kind of what the idea is, show you examples, and then there's probably be a lot of questions afterward. So what are containers? So a container is a software container. So it is taking code and then everything needed to run that code, packaging it up in a bundle, and then sharing it with my friend or my colleague. And they can just, on their computer, hit run, and then in hopes that it just runs. So that is the idea of containers. And the most well-known brand name of container software is Docker. And so I think that's a really good analogy. So the analogy is you could think of software containers as like a shipping container, right? Shipping containers move cargo around the world. Docker can move cargo around the world and does it in a standard way. But for the shipping container to be offloaded and executed, i.e. ran on someone's computer, that shipping port needs to have Docker. And so every computer, we all have Docker. We can take any kind of software, put it in a container, ship it over to any computer in the world. And if that computer has Docker, we can just say Docker run, and it's going to run your code. And so it eliminates the need to try to install, complicated setups or complicated computing environments on your own computer to run someone else's code. And so Docker has gotten a lot of traction in the software development world. So if you go to Docker Hub or just Google, you can find all kinds of software that available in a Docker container. I can find QGIS in a Docker container. I can find GDAL in a Docker container. And so if I find, a software that I like QGIS, I can go to my computer and I can pretty much just say, Docker run QGIS, and up pops QGIS. And I did not install QGIS on my local machine, but everything needed to run that software, it came to me in a container. Tyler asks, is there a link to Cypress's full Docker training somewhere? Michele, maybe you could provide a little bit of guidance for Tyler. What's that?
Can I say something?
Sure. Yeah, you would like to unmute and say something?
Hi, Tyler. Thank you for the interest. I'm happy to share with you some of our documentation on containers. We used to run something called Container Camp, and we still have all of the materials. It's slightly dated now. We haven't been running Container Camp in a while, but I can send you a couple of links that may be useful for you. And by all means, you can always reach out to us by mail. So any question that you might have about containers, we are able to answer. Thanks.
Thank you, Michele. Okay, so what are we doing? We are gonna, I've already built a reproducible containerized pipeline to do something, and I'm gonna share it with you guys. And it's gonna be very easy. You're just gonna basically essentially clone a repo from GitHub, and you're gonna go to a command line and you're gonna say Docker compose up. So it's like one command to run a whole pipeline of stuff. Okay, what else about Docker? Docker is, it's a type of virtualization. So here we have a graphic showing the difference between a virtual machine and a software container. A virtual machine has everything. It is like an entire operating system and everything needed for a computer. A container is lighter weight. It doesn't have its own operating system. So it operates on the host machine's OS. But other than that, it's sort of similar. It's a virtualization. Anything interested in the chat? Okay, yeah, thank you very much, Carlos. There's someone that, yeah, thank you for admitting them. Okay, so containers for reproducible science. So why are we doing this? I think I kind of alluded to it. Containers are great because they encapsulate a software environment, ensuring that it has the same versions of software, libraries, and dependencies are all packaged up. And then that package can be, put on basically into a marketplace online. The most common place to do that is Docker Hub. There's a lot of other repositories for containers. And then anyone can just go to those websites and pull them off the shelf and run them. So it becomes like a library of code that can be more easily ran on any computer. That's the idea. So it's easy to share. And in theory, platform independence. So yeah, the idea is that we could run these across operating systems also. That is not always the case, and there's always caveats. If you are making containers and you're using ARM, like a more what they call Apple Silicon, so a more a new version of the processors in Apple computers, it might not work with Linux or AMD 64. It might not work with Windows. So there could be some little caveats there, but the idea and the theory is that if we can make a container, it should be able to be run on any computer, anywhere, any OS. Not always true, but that's what we want. That is like our vision. Okay, we've talked about Docker. Docker Hub is the world's largest repository of container images. You can think of it like the GitHub for containers. If GitHub is mostly about sharing computer code, Docker Hub is where you share container images. Most of them are open and just downloadable or runnable on your computer. All right, so let's get to our containerized pipeline example to give you an idea of how this actually works. All right, so we're gonna take an example from my professional life, which is drone data. And we are going to do this little pipeline right here. So we're not going to collect the data. I already did that, but we're going to skip that. And we're going to take the drone data and we're going to put it into a containerized version of Open Drone Map. So Open Drone Map is a photogrammetry or structure from motion photogrammetry software that will take a series of two-dimensional overlapping aerial images and create maps out of it. It'll create orthomosaics. It'll also create point clouds and kind of other 3D type imagery products. So Open Drone Map, or ODM, is also similar to Pix4D, also similar to Agisoft Metashape. So ODM is like the open source version of all that. Metashape and Pix4D are commercial and proprietary. And ODM, Open Drone Map, is open, as the name suggests. So we're going to take drone imagery, run it in a Docker container that will then produce some imagery products using Open Drone Map. The output of that is then going to get passed into a command line tool called PDAL, where it's going to do some point filtering. All right, so we're going to take all the points that are in a point cloud and we're going to identify what are ground points and what are tree points or non-ground points. So that's a very typical thing you do with point cloud analysis. You separate them into two things. What are points that represent the ground and what are points that represent the trees and the houses and everything that is not ground. So that's what the pipeline is. And we're going to end up with a classified point cloud showing what is ground and what is non-ground. So that's our pipeline. So that actually contains two containers. And we are stringing the containers together with something called Docker Compose. If you think of a containerized script as like a modular piece of code, we can string multiple containers one after another to build any kind of customizable pipeline you would like. So in this case, we have two containers. One is ODM, or Open Drone Map, and one is PDAL.
Question.
Yes, Michele, what is your question?
So, let's say that you have money. There's a single software that would be able to do the same thing that you're doing here, or would you still have to go through something?
The question was, to do what I'm doing here, would you need, does it exist one software that can do all this stuff instead of building this modular pipeline? In my experience, no, not really. There's not really one software to do it all. I find that software in the geographic or geospatial analysis often is good at like a few things, and that using a series of tools usually, at least in my case, is usually a better thing to do. That also brings up is like, the way I'm doing this is one way to do a pipeline. Instead of this, the whole thing could be one long Python script. I'm not saying you can't do that. You can make a one monolithic Python script or R script to do this stuff. And you could also call that a pipeline. But here I'm really trying to emphasize reproducibility and handing it over to a friend who all I have to do is hit run essentially, and it works. And I'm more interested in emphasizing open science also. And I like the whole idea of modular code that can be rearranged kind of in any order that you want. And so this is just like kind of a small example of that. All right, so to actually get to the pipeline, we have to click into a different repository. So please click with me. This is going to github.com/JeffGillen/geospatial pipeline. Go ahead and open the link in a new tab. Okay, I already kind of explained the pipeline. We have two containers. One's going to be Open Drone Map, which does photogrammetry, which creates a point cloud. And then it passes it to container number 2, which is PDAL, which does point cloud analysis. In this case, it's going to classify points as being of the ground or being not of the ground. All right, so the mechanics of how we do this. There are two ways. You could clone this repository to your local machine if you want to do it locally. Keep in mind, you're going to be downloading about 32 JPEG images drone images. You don't want that, 300 megabytes or something of data. You don't have to do it to your local machine. Alternatively, if you would not like to use it on your local machine, we can do it through code spaces. So if you've never used code spaces, directly in a GitHub repository, we can click a button and we can start a virtual machine and start doing some computing. So for my demo, that's what I'm going to do. All I have to do is go up here, this code button here, hit code spaces. And then from here, I can launch a virtual machine. Let's see. Click that button. No, that's not what I want to do. I was looking for, there's a button where you can choose the size of the VM.
Go back,
Yeah, let's do that.
then the three dots on the right.
These are the three dots.
Yeah, and new with options.
New with options. Okay, there we go. Okay. Thank you, Michele.
No problem.
So new with
You have to be
options.
signed in, right?
What's that?
You have to be signed in.
You have to be signed in, yeah. You have to have a GitHub account. Okay, so for my geospatial pipeline repo, I've started a new code space, but I get to choose like how big the machine is. I'm gonna do big, just so it'll go quicker. 16 core. All just CPU, so no GPU involved here. All right, create code space. So this is going to create a new virtual machine, or I can very easily run my pipeline. And you could just as easily do this on your local computer. Okay, so here we are. Are you there? Are you there, Kamal?
Well, I have to log in, so I think you can have to bear with me.
Okay. No problem. No problem.
Can you take us back to that step where you click on the green button?
Yeah. Yes, I can.
Thank you.
Let's see. Right back here. Okay, so go back. All right, so the Jeff Gillen / geospatial pipeline repo, are you here? All right, so this green button, code, you would drop it down and you would hit the 3-dot menu, and in that, new with options. And so then once you do that, then you can choose how big of machine type you would like. And for it to run quickly in our little short hour, I would do 16 core. All right, what do we have going on in the chat here? Ah, Michele, okay, you're doing some
Yeah,
help with Tyler. Great. Tyler's over in Colorado.
maybe to go back to container stuff and refresh.
Yep. Okay. Where you at, Kamal? Is it launching
Yeah, it's doing some stuff.
your VM? Okay.
Alright, good, I mean.
So yeah, Codespaces is nice because you can launch a VM just directly from a repository, and then it has everything in your repository just right there for you. All right, so I'll just go ahead and do the command here. So it's one command basically to do this. It is docker-compose up. That's all. When I type that command docker compose up, it's going to start my Docker pipeline, and it's just going to run it as I, specified it to be run, and it's going to output things. So it's a one-click pipeline that I can then share with anyone. I'm sharing it with you guys. It's very easy. So Docker compose up, run. Okay, so this will take a few minutes. So you imagine, I had to make it smaller. I tried it last week and it was taking like 15 minutes. So I was like, oh, let's make it smaller. So it only has 32 images in it. Yes, chat. Can you save output on your local computer? From code spaces?
You can click.
You can run locally connected to the.
Yeah, I mean, the answer, Pradhan, is yes. How would you do that? You would, so if I'm in code spaces, I would push the results back to GitHub. And then from there, you could download it from GitHub, but there's probably a direct download from code spaces.
If you
Yeah.
right click any of the files you have there, you can download.
Okay, so like, oops, allow. Yeah, we have download, yes. So anything that is on our virtual machine here on code spaces looks like you can just download to your local machine anytime you want. Do you need to be the owner of repo and those use GitHub's VM? No. No, you guys are not the owner of my repository yet. You're still using it. Because you guys do not have edit, you cannot edit my repository. As you are working in code spaces and you're producing document, whatever, you're doing any kind of thing, you're not actually changing my GitHub repository. It's just existing here in this virtual machine. And so if this virtual machine closes down, nothing's going to be saved. And my GitHub repo has been unchanged. So none of you have edit abilities for my repo, but you can launch a VM and pull the documents or data that I have and use them. Okay, so how's my going? How's it going? Ah, okay, where's the input data located? Great question. Okay, now that things are running, what is going on here? Okay, so the pipeline is consisted of two containers, right? The OpenDrone container and the PDAL container, and both of those are located on Docker Hub. And so when I say Docker Compose up, it is actually going to those web repositories and pulling those containers to the virtual machine. Okay, where's the data? The data is actually right here in the repository. You could change that. You could bring your own data. You could say, oh, the data is over on this server. The data is on your local. So the data can come from anywhere. And for our example here, I just thought it'd be easiest if I put all the images, our data, just here in the GitHub repo. Ah, looks like I ran out of memory. Let's see, max tiles exceeded. This is a strong indicator that reconstruction failed and would probably run out of memory trying to process this, gracefully stopping. ODM did not complete successfully. Exit 1. Okay, interesting. I'm curious if others get the same thing. I've ran this several times before and it never had this problem, but live demo. Alan, can you download or clone the Docker images in the repo to Cyverse to use as tools to build Cyverse containers or applications? Yes. What the Cyverse discovery environment is running containers. So the containers need to be in Cyverse's container registry or repository called Harbor. But that's how all the applications in Cyverse run, is they are sitting in as a container image. And then when you go and click and be like, launch Jupyter or launch whatever, it will run the container and that's what you're seeing. So yes, Alan, you can make your own custom containers that are for whatever you are interested in running. So yeah, I'm interested if anyone else is able to Still running. Okay. Yep. It usually takes 5-6 minutes, something like that. Or it just fails like me. Michele.
Repository for drone images. Sorry, my bad. For NextGen Geospatial Docker images.
Is there a repository for
Kind of like Anaconda or
no, Michele was asking, is there like a popular repository where you can find a bunch of geospatial type containers or container images? No, not really that I know of, not specifically. So I came from the world of geospatial, and yeah, it wasn't really, I had never learned about this technology until I started working around software engineers and people that are more like data science involved. And then I'm like, wow, that's how you do it. It ran all the way through. Excellent. Okay, excellent. Would you like to share your screen, Michele?
Yes, I can. But you'll have to drive.
Okay. Yep. Let's see. I'll stop share. Okay, so yeah, why don't you make the terminal a little bigger? Okay, great. Okay, yeah, so Michele's went all the way through. And so when you finish Open Drone Map, it makes this nice little graphic, which means you were successful. Why mine didn't work, I don't know. Because the live demo gods hate me. It's not the first time. Okay, so it went all the way through and essentially worked. Let us see here. Let me go back. Yeah. Thank you very much. So let's get the results here. Yeah, bear with me a second. All right, so when Michele finished, what it did, so the first container did photogrammetry. It created a point cloud, and it created a point cloud as a cloud optimized point cloud. Remember, we talked about that a couple weeks ago. So it's creating that, and then it passes it over to the second container, which is PDAL. And what did it do? It did the filtering. So it identified what points were ground and what points were non-ground, and outputted all these things. And so you're sharing there. Yep. And so you notice on our directory here, our repo, we have a whole bunch of new stuff. That was mostly done through Open Drone Map. And if I go into ODM georeferencing, here's some things that it made. And this is the final thing that we want. Something called ODM georeference model filter.copc.laz. That's a long one. How do I do a right click? I want to download that. Thank you. So I'm going to download that to my local machine here. And then let's
You want to send this to you?
Yeah, sure. Well, it might be a little big, so no, let's just do it on your screen. So go to here. So now we're going to look at it. So just to prove that this works. Yeah, just open a new browser tab.
It's in the chat anyway, so
Okay,
let me
and go to
course content.
what's down here?
View code.
Yeah, you're gonna have to do several clicks to get where I'm at.
Nope, that's okay.
Yeah, then here.
Then here.
Yep.
And
then keep going down. Yep,
viewer
that
course.
one.
Okay.
Yes.
Okay.
Okay, so this is a cloud optimized point cloud viewer. It's a web viewer. So we've made a cloud optimized point cloud, and now let's just check it out. So let's add that data. I believe it's going to be
This one?
yeah, click that one. Yep. I think You could maybe drag and drop or add it,
Or I can also add as a URL. Okay, I'll drag and drop for now.
drag and drop.
Here?
Yep, I think.
Whoa.
There we go.
Oh.
Okay, so yeah, I don't know how to, I'm helpless without a mouse. Let's be honest.
Okay. You want me to zoom in?
I want you to tilt.
tilt. Can
Yeah,
I
I don't-
close this? Oh, I can just click this.
Yep.
Tilt.
Yeah, I don't know. So we are in a mouse is very useful when you're in like a 3D environment like this. Good idea.
Sir. There you go.
I don't know what it's doing. Okay, so this is what we've created with our pipeline. This is a three-dimensional. Okay, did yours die also?
Didn't die, just complained, yeah.
Okay.
Were you doing it? You're doing it on code space?
Yeah.
Okay. Yep. Elevation. So this is what we created. It's not going to be very pretty because you know, couldn't have that much data, but we've created a three-dimensional point cloud of a golf course. So that's what in container 1 did, right? And then container 2 was the filtering, right? So let's just show that. I can go over my menu here. I can change it from RGB to classification. Ooh. And here's what container 2 did. It looked at all the points in my point cloud, and based on some rules, it used an algorithm called cloth simulation filtering. And it identified all points as being either the ground or non-ground. So all the trees ended up being classified as non-ground. Go back to red, green, blue. So yeah, this is a really handy viewer. Just great to kind of share with your friends. So if you have a cloud optimized point cloud, you can just copy a URL, you know, with this website and then, you know, send it over to your buddies and share. Okay, so that is what we did. So let's go back and talk about Docker a little bit more. Thank you, Michele. All right, so how many people actually were able to get through it without it crashing? Anybody here? Were you able to get through it all the way using code spaces?
Yeah.
Okay.
I'm done too.
Yours worked also?
Yeah, it did, but it did get to the end.
Yay. Okay, yeah, so that was just an easy, simple demonstration of running 2 containerized pieces of software sequentially. And how did we do that? We use something called Docker Compose. So Docker is the technology that containerizes it, and then Compose is kind of like configuration that sits above Docker and allows you to kind of manipulate how multiple containers can work together. And so it works like it's a YAML file, YML file, Docker Compose. And so this is the thing I created to orchestrate this pipeline. So it's really simple. This is the entire thing. In it specifies the services, and the services are the 2 different containers. We used Open Drone Map. And here is kind of like the commands in Open Drone Map, you know, to get the output that we are interested in. And then the second service is PDAL. So that's what this stuff here is PDAL. So there is a lot of details about software containerization and pipelines. You know, it's really an infinite field. There's a lot to it, but hopefully this was just kind of a simple demonstration showing that One, what is containers? It's a great way to share analysis and code with people without them having to like set up, do the entire setup or, have an environment that matches yours. So there's just an easy way to share code from one person to another, from one computer to another. And yeah, you can use it as a way to start building your pipelines. You can make it as simple or as complex as you want. The bioinformatic people, they have really taken it to extremes. Like, I feel like they've kind of invented this space. And Docker Compose is simple. It's more like one container leads to container 2, which could lead to container 3. If you use programs like Nextflow or Makeflow or SnakeMake, it can be like branching stuff, like really complex. Like, you could start with one input and it could branch to 5 different step 1s, which can then branch to 2 different step 2s or something. So it can be, much more complex in terms of your processing map or your workflow that you're trying to create. Yeah, so hopefully this Docker Compose made sense. And yeah, it just shows you a little different way to write automation. It doesn't have to be just one monolithic R script or one monolithic Python script. You can containerize to make it easier to share with your friends, and you can make it modular. So you can create one little container that does one little thing and put it on the shelf for someone to take off the shelf and then combine in any kind of order they would like for whatever their processing purposes are. And so I will leave it at that. Is there any questions?
In the process of creating the containers, the ones that you showed us,
Mhm.
is it something time consuming? Is it like a resource intensive? It gets spent a lot of time getting the things, or just like push the steps, that's it?
Okay, yeah, running containers is very easy. You guys ran a container, super easy. Building containers is harder. That's like a next level of like, okay, if you would like to actually build one yourself, yes, that's like another skill set. Like most things in software, you start with what someone else did and build on them. And so in GitHub, you can find all kinds of Docker files, is what they're called. It's the recipe file to make a container image. In my repos, the ones that you guys visited have Docker files. And so that's the actual file that it's like the recipe for how to make a container. Yeah, it is like kind of the next level, but it's achievable. Like, I figured it out somehow, and that's saying a lot.
But then the resulting container, is that very modular? I mean, is it something that you could give to someone and then you can modify themselves to make some other stuff?
When something is a container, usually it's set. It's like, it is what it is. They can take the recipe, the Docker file, and then change it any way they want to make a new Docker image.
But I thought I heard you saying that you could have imported your own images and run that very same container, no?
Yes, the containers do not have data in them.
Oh.
The containers is just the code and everything you need to run that code. The data in this case, I just had it stashed in the GitHub repo. That data, so typically with containers, you bring your data to the pipeline. And so you could get a pipeline, containerized pipeline from Docker Hub. It's on your local machine. Your data on your local machine can go right into it. And there's a real one line of code to be like, that's the data that goes in.
If I may add,
Sure, Michele.
when you were saying modular, you were
Mhm.
talking about Docker Compose.
Sure.
And Docker Compose is very modular in the sense that you have 1, 2, 3 containers. And you can put one in between 1 and 2, an extra one in between 2 and 3. And it will follow that specific workflow that you have inside it. So Docker images, when they're created, those are set, as Jack was saying. Docker Compose is a little bit more, well, not a little bit, it's a lot more modular in a sense that you can have as many containers as you want. within that specific work.
Yeah, and run in the sequence that you want. You can think of Docker, a container as like a brick. And you can't change the brick itself, but you can put the bricks in different orders to make the house. It's okay. Well, thank you all very much. And this is recorded. Oh yeah, the survey. One final thing. If I could get anybody that's interested in providing a little bit of feedback, we very much take it seriously. So on my homepage with the content, I'm not sharing my screen, am I? Nope. I need to share my screen. Okay, on my course website on GitHub, I do have a little feedback form. If you could say nice things or tell me it was terrible, or anyway, any feedback is useful to us. So please do say something. Next week, what are we doing next week? Let's look at the calendar. Yes, I think we have 2 more after this. All right, so we did reproducible pipelines. Next week, I'm going to talk about geospatial data APIs. And so that is the idea that to get data, you don't necessarily have to go to a website and click through a graphical user interface. To get data, you can do it programmatically through APIs. And I'm going to give you an example of getting data from Planet. So the University of Arizona has a very large campus-wide Planet license. So if you are doing any kind of satellite remote sensing, you can get a whole lot of free data because we've already paid for it and we would like people to use it. And so that's what next week is, how to kind of automate and programmatically pull data from Planet into a Python environment. And then the final session is October 29th, and I'm going to do a session on spatial temporal asset catalogs, or STAC. And STAC is an open source way of trying to, I guess, make a catalog. It's essentially metadata for geospatial data. Yeah, and it's trying to make like kind of a global catalog. And can we all get on the same page in terms of standardizing what technology or how we describe geospatial data so it's easier to find across the web? And spatial temporal asset catalogs has really gotten a lot of traction. I don't think it's big in academia yet, but more in like geospatial companies. Planet is using it, Microsoft Planetary Computer. I think there's NASA, I think, also has a STAC catalog. So yeah, the last session will be all about STAC. And then we are done, guys. So thank you very much for tuning in, and the recording usually arrives on Friday. Thank you very much. We'll see you next week.